In this section, we'll look inside RMT itself to see how it works, especially how NFRs are calculated for different risks. This brings together many of the concepts from the previous sections. Firstly, to perform reserve calculations for a given trading period, RMT needs to know the schedule for that period as produced by SPD. Then, RMT also needs to know what the operating configuration and constraints on the HVDC link are during the given trading period. There's also a range of configuration data that can influence RMT calculations. These data may be altered by the system operator when required. Each time it solves for a trading period, RMT calculates the risk setter FIR and SIR for each type of risk: ACCE, Dcce, Dcece, and ACECE. It does this for both the North and South Islands. At the heart of RMT is a calculation and simulation engine containing a model of the New Zealand power system. Parameters representing the state of the system can be fed into the model, and it predicts how the system will react. When RMT runs, it reads in the relevant schedule from the market database. RMT is also aware of any constraints on the HVDC link during the trading period in question. The first calculation concerns the fast instantaneous reserve, or FIR, for a North Island AC contingent event. An ACCE is typically the loss of the largest single unit of generation, but AC risk groups can also be the ACCE risk setter. To do this, RMT checks the schedule to see how much power and reserve are scheduled for each generator in the North Island. The ACCE risk setter is identified by checking which generator is scheduled to produce the most power plus reserve. The simulation engine is set to mimic the generation dispatched on the system for the trading period. RMT can now start an iterative calculation, which it begins by using the simulator to model the starting condition that the risk setter has tripped, and the amount of FIR scheduled is equal to the amount of risk minus the previous NFR, or the FIR in the schedule if there is no previous NFR available. The simulator produces a representation of a frequency trace. In this example, the frequency dips only part way when the risk setter trips. It is permissible for the frequency to dip as low as 48 Hz for a contingent event. This means it's possible to schedule less FIR and still stay above the limit. In the next iteration, the simulator is set to model much less FIR when the risk setter trips. The simulator shows that this small amount of FIR results in the frequency dropping below 48 Hz. Therefore, not enough FIR has been scheduled. The amount of FIR modelled has adjusted over several iterations to get closer to the minimum frequency limit. After several iterations, the frequency should be close to, but not below, 48 Hz, provided there is enough FIR available to cover the ACCE risk. RMT can now convert the FIR required into the FIR net free reserve, or FIR NFR, for the ACCE risk in the North Island. It does this by subtracting the FIR required from the risk. RMT now moves on to calculate the sustained instantaneous reserve, or SIR requirement for the same ACCE risk. The SIR required is procured 1-to-1 to the risk, but it could be more if other generation has tripped. RMT converts the SIR required into the SIR NFR. It does this by subtracting the SIR required from the risk. In this case, the SIR NFR is 0. We will now look at the Dcce calculation. A DC contingent event is the loss of a single HVDC pole under bipole operation. To calculate the Dcce risk, RMT checks how much power is to be transmitted over the HVDC link. A risk subtractor is calculated using a number of factors, and it includes the overall capability of the remaining HVDC pole. The risk subtractor is only available in bipole operation, that is, when both poles are in service. The Dcce risk is then found by subtracting this value from the HVDC megawatts received. RMT then performs the iterative simulation to calculate the FIR required for a Dcce risk. RMT converts Dcce FIR required into the FIR NFR. This is done by subtracting the Dcce FIR and the risk subtractor from the Dcce risk. So effectively, the risk subtractor forms a part of the Dcce FIR NFR calculation. We will now look at how the SIR is calculated for a DC contingent event. RMT converts the Dcce SIR required into the DC SIR NFR. It does this by subtracting the SIR required from the risk. Because the amount of SIR required is equal to the amount of risk, the SIR NFR is 0. A DC extended contingent event is the loss of both HVDC poles under bipole operation. An AC extended contingent event is defined on a station basis, and that can include losing an interconnected transformer or a busbar fault, which could be the loss of multiple generators. Here, we'll show how RMT calculates the reserve requirements for a DC ECE, but it uses a similar process when calculating the reserve requirements for an AC ECE. The North Island DC ECE risk is equal to the total HVDC megawatts transfer received in the North Island. RMT takes into account automatic under-frequency load shedding, or AUFLs, when calculating reserve requirements for extended contingent events. The iterative simulation is performed to calculate the FIR required for an ECE. The FIR required is subtracted from the risk. Remember, AUFLs forms part of the calculation for the ECE FIR NFR. The ECE SIR requirement also takes into account AUFLs, as NFR SIR and therefore the amount of SIR required is similar to the amount of FIR required. As a result, the ECE SIR NFR is similar to the ECE FIR NFR. Once all the reserve requirement for the North Island is calculated, RMT moves on to produce the reserve requirement for the South Island. RMT sends the NFR values back to SPD to offset the real-time risk. A simple formula to remember is that FIR required equals the identified risk minus its calculated NFR for each type of risk. And the more NFR that is available, the less FIR is required. In this case, North Island ACCE requires the most reserve, so FIR is scheduled to cover the ACCE risk in the North Island. Under the National Market for Instantaneous Reserves, or NMIR, this reserve can be procured in both islands for an AC risk. RMT models both islands together in its reserve calculations. For DC risks, the total amount of reserve must be procured in the receiving island.